Here is an example of an AC signal. The A in AC stands for alternating. In this case, we have a signal whose amplitude, which is the level in this direction or this direction, is oscillating. It's going up, and then it's going down, it's going up, and then it's going down. In this case, it's oscillating about the zero line. Okay, so sometimes the signal is positive in this region, then it's negative, and then it's positive again, and then it's negative. And the thing to appreciate about this diagram is that it represents how the signal changes with time. So at time 0, let's say here, in this case, this signal has a value 0. And then as time goes on, the signal rises and rises and rises until at time B it reaches the maximum value, and then it falls back again until at time C it falls to 0, going from a positive value through to a negative value. And it continues to fall until at time D, that's D here, it's reached its maximum negative value. At that point it starts to climb again, and then goes from negative through 0 to positive values again, and now it starts to repeat itself. So that's the other thing about an alternating signal. Generally speaking, we're talking about periodic signals. That means signals that have a period. In this case, we've labelled this one with a big symbol T, a symbol big T, indicating the time it takes for this signal to repeat itself, the repeat time of the signal. And you see that it does the same thing again. Okay? And we'd expect it to go on doing that again and again and again as time went on and on. So this is just a snapshot over a brief period of time of how the signal is varying. That period T there, that's the standard symbol for period of an alternating signal, can be taken from between any 2 points, between any point and the next point along in time at which the signal is doing the same thing. So that means having the same amplitude. So in this case, if we start here, having a 0 amplitude again, but unlike here, doing the same thing as well. So that means in this case going from negative to positive values, as it was there, from negative through to positive values. That point in the middle there, while the signal amplitude is again 0, in that case though the signal was going from positive to negative, so it was changing in the opposite direction to here and here. So if you start here, that's the next point at which the signal is having the same value as it had at that point and doing the same thing. So that we call the period. And clearly that period can be taken between any 2 points where that condition is satisfied. So between 2 crests, between one trough and the next trough, and those are the ones that are the most easy to pick up in a diagram, but you could pick any point inside, for example that point, and go forward to that point, because that would be the next point at which the signal was doing the same thing, having the same amplitude, this value here, and falling in the same direction. Okay, so that's the meaning of the word period. I mentioned amplitude just then. That's an indication of how big the signal is in this direction. Okay, so you can actually talk about that in a number of ways. Here I've labelled it with V0 there, V subscript 0, and there's that little dotted line there which takes us to the peak. That's the vertical distance, in this case in volts, if we're talking about V. It could be anything, it depends what you're plotting. Here I'm plotting a voltage. It's the distance between the 0 line and the maximum value of the curve. So it's the maximum value, if you like, that the signal takes. So that's the 0 to peak amplitude. And mathematically, and that's actually how this curve might look if we were to represent it mathematically, ignore that if you want at the moment, but you can see that V0 cropping up there. So the 0 to peak amplitude is the one that's most useful if we wanted to talk about this thing in a mathematical way. Practically, though, there are 2 other amplitudes which are of either one's of importance and one's easy to measure. The one that's easy to measure is the the peak to peak amplitude. That's from the peak here down to the peak at the bottom there. So the vertical distance in volts between the negative maximum and the positive maximum. And when I say it's easy to measure, that's the one that you can most easily pick off an oscilloscope screen. And actually there's a simple relationship between the two, as you can probably see, in that the peak-to-peak voltage, the peak-to-peak amplitude, is simply twice the 0 to peak one. Okay, quite straightforward. Now there's another one called the root mean square voltage, which I'll talk about on another slide. But that one, the root mean square voltage, is actually the 0 to peak voltage divided by the square root of 2. It's the one that is most useful when it comes to calculating delivered power by electrical signals. And actually, in your renewables course, that's the one that I would most try to get a handle on what that one's about. But we'll save that for another slide.